Hi, y'all. This is Mel again. Welcome to Heat and Mass Transfer. Today we're going to be covering problem 6.004 out of the textbook. So in this one, we're given that water at bulk temperature 25 degrees Celsius flows over a stainless steel wall AISI 302. We know the temperature of the steel wall at one surface. We know the thickness and we know the surface temperature opposite the water. So it's a wall, and on one side it's got water, and it's got a surface temperature that's held at the other side. We know that what we're trying to find is a convection coefficient associated with the water flow under steady state conditions. So it's the transient system, or not, it's not a transient system. We're trying to find the temperature gradient in the wall. We're trying to find the temperature gradient in the water that is in contact with the wall, which is the thermal boundary layer. And we also need to sketch those temperature distributions from B and C. So we're assuming again, steady state, negligible radiation, that the wall conduction is described by a plane wall conduction just because we don't, quality of life, and also it's a pretty fair assumption, it's a wall. We have the wall properties from the back of the textbook. Here's the wall properties at 300 K for AISI 302. We have no heat generated within the wall. The flow is laminar and incompressible. Quality of life assumptions. We're also assuming that the water properties are from the saturated water table at bulk temperature 25 C, which is about 300 K. You can find other properties. This is just what I had on hand. So here's the solution. Just to myself, I put this little note here for the what's it called? Sorry, the thermal resistance circuit, thermal circuits, right? But you don't really need to do that. I just put that as a visualization for myself. And what you can actually do is you can do a surface energy balance at the surface where the water is flowing. Um, because it's a surface energy balance, we're not going to have any heat generation, and it's steady state, and it's a surface energy balance, so there's definitely no energy stored. So what we're going to do from there is that means that E in is equal to E out, and the in, if we're at that border and we're transferring heat from the wall to the water, what that means is that we are going to have convection into this surface, or not convection, conduction from the wall into the surface, and convection from the wall to the water. So that means we've got some heat flux equations here. This is the same as the heat equations, but it's flux because we took out the area, so it's per meter squared. We've got our little equations, set them equal to each other based on our surface energy balance, do a little bit of math, and calculate an H of about 1200 watts per meter squared Kelvin. For forced convection with the liquid, that seems about right. So now we're going to try and find the temperature profile of the conduction. We know just in general that plane conduction is a linear profile. What we can do is if we say, oh, Q double prime, which is our flux, is equal to K dt dx, we do a little bit of integrating and move stuff around. We end up with and we also know that the heat flux is constant because it's steady state. We also know that it's because of our surface energy balance that the amount of heat flux coming in from the wall is the same as the opposite of what's leaving in the water. So we know that this is going to be equal to whatever we get over here. And so from there, we can calculate a heat flux, just a general heat flux across that surface. And with this equation here, because this is our Q double prime, we have T of X is equal to Q double prime divided by K times X plus C, because we integrated this from 0 to X. We have our condition at X equals 0, which should have been labeled TS2. This is the side that's exposed to water. This is the side that is not. We know that's 100 degrees C. So we know that actually ends up being C, because if X equals 0, this term goes away. We can sanity check ourselves and say, okay, at L, which we know is 0.05, given this value that we calculated earlier, plus RC, do we get 40 degrees Celsius? And we do, so that's nice. Then we say, okay, so now that we've sanity checked ourselves and everything seems okay, we have our temperature profile as a function of distance in the wall is equal to negative 1200 X plus 100 degrees C. So now for the boundary layer, this is an equation you can find in the textbook. It's basically that you can approximate, it's sort of approximate, sort of not really. You can represent, actually represent is a better word to use here than approximate. You can represent the fluid layers that are very close to the surface as um, that the heat flow is due to conduction in the fluid as opposed to convection within the fluid. Um, and so you end up actually being able to apply Fourier's law. And if you do that, you get this value for H. You can use H as a sort of a Fourier law representation at the contact between the fluid and the surface. We also know delta T, which is the thermal boundary layer thickness, is just generally when the temperature change is pretty close to the dimensionless temperature change is pretty close to 1. So what we end up doing here is pretty similar. We've got our convective heat transfer coefficient here. We've got properties. This is again stolen from the book. For our this is the thermal conductivity of the fluid. We've got our temperature difference from the surface to the fluid, the bulk fluid. We've got our little thing. We can calculate that at dt dy of y equals 0, just moving stuff around in here, we get this constant here, that the change in temperature per change in height away from the surface is this negative 2.956 E4 times 10, times 10 to the fourth. We also know from this delta T equation that we can calculate our temperature at the border where at the end of the boundary layer thickness. At the end of the sort of like the edge of the thermal boundary layer where it goes from thermal boundary layer to like fully thermally developed. And it's another matter of, okay, we've got a linear equation because it is Fourier. We've got our linear equation, we've got our slope, our variable, and our constant. We have our boundary condition of T of 0 is equal to the surface temperature. We know that, so that gets us C. We get this equation T of Y. And then from there, we can just calculate a height, like a boundary layer height, given this temperature at that height and this constant here and our constant here as well. Our slope and our y-intercept for the y equals mx plus b people out there. So again, when we sketch this, they're both linear. If we have our plane wall, we've got our TS2 and our TS1. Again, the water flow is on the right side. Apologies for not sketching that. And we've got our thing 0x towards the right, and then this is a distance L. We know that's linear and it is decreasing, which we can actually show here because it's got the positive y-intercept and the negative slope. And it's going to be the same thing with the fluid surface contact area. So we've got our y and our temperature as a function of y. Oh, those axes are backwards. My apologies. But long story short, it's linear, it's decreasing. We know that this should actually be T of y and this should be y. The axes are flipped. We can see here that the temperature is decreasing linearly from surface temperature to boundary layer temperature, which boundary layer temperature is pretty close. 25.15 is pretty close to our 25 degrees for our bulk fluid temperature. Yeah, that's it. Thanks for coming.